Pandas turns raw numbers into labeled data. A series is one labeled column. A data frame is a labeled table. Every row has an index label and every column has a name, so selections are explicit and readable. Selections by label use loc. Selections by position use iloc. Missing entries show up as nay-in. Pandas is built on NumPy, so math is vectorized and fast. And when two objects share labels, Pandas aligns by label before it calculates. That's why results keep the right rows and columns even when orders differ. A series with values 250, 450, 300, and 200 is created and printed. The left side shows the default index 0 through 3. The dtype is integer because all entries are integers. This printout emphasizes that labels matter in Pandas. The item at position 1 is retrieved with iloc 1 and the value 450 appears. iloc is strictly position-based. With the default integer index, label 1 happens to match position 1. A series that mixes text and numbers appears with dtype object. Math on mixed objects slows down or behaves differently, which is why numeric work prefers a numeric dtype. A series of names appears as dtype object, but now homogeneous. This is fine for labels since arithmetic is not intended. The cell series is rebuilt with index labels Q1 to Q4. Printing now shows meaningful labels on the left. From this point, label-based selection becomes clearer than remembering positions. LOC-Q1 returns the Q1 value because LOC uses labels. iloc-1 still returns the second entry by position. After switching to string labels, Series 1 would look for the label 1 and fail. This is the common pitfall that LOC and iloc avoid. The expression sales greater than 300 yields a labeled Boolean mask. Applying it returns only quarters above 300 and preserves their labels. The preservation happens because filtering aligns the mask to the index. We treat a data frame as a two-dimensional labeled table. Columns can have different types, like a spreadsheet or a dictionary of series. That's why we can name columns, label rows, and still do fast vectorized work. We see 3 columns and 3 rows. Dictionary keys became column names, and Pandas assigned default row labels 0, 1, 2. Different dtypes per column are okay because a data frame stores columns independently. One column appears as a labeled series. The left side is the row index, and the line name product shows the column name carried with the series. LOC uses labels, here the label 0, while iloc uses integer positions. They look similar only because our current index labels are numbers. Row labels are now strings P1, P3. So, looking for label 2 fails with a key error. This is why we keep label versus position access explicit. iloc P3 works because it matches the string label. iloc 2 still returns the third row by position. 2 valid paths, label or position. Data cleaning prepares data by handling values that are missing, wrong, or poorly formatted. Pandas provides built-ins for these tasks. Missing entries appear as nan for numbers and none for text. That's Pandas' standard representation of absent data. Only complete rows remain. This is strict and quick but may discard useful information. Row count is preserved. Missing product is unknown and missing price becomes 0, which keeps downstream joins and groupbys intact. We verify that product is object and price is float. Explicit casting keeps arithmetic predictable. We built a labeled table, practiced label versus position access, then cleaned missing values by dropping or filling, and confirmed types so later analysis stays stable. Data manipulation in Pandas covers sorting, grouping, merging, and pivoting, changing layout, and aggregating values so the table answers our questions. We sort rows by price from highest to lowest. The rows are reordered, but the data in each row stays together because sorting operates row-wise on the chosen column. The groupby function in Pandas is a powerful tool for grouping data by one or more columns and then performing operations like aggregation, transformation, or filtering on each group. This table gives us region, product, and sales. We'll reuse it to demonstrate totals, multi-key groups, and multi-stat dashboards. Pandas sums sales within each group and returns a series whose index is the region label. That index change is why the result prints as totals per region. Two keys create a two-level index, region then product. Each pair gets its own sum. The hierarchical index explains the stacked row labels we see. We keep the same grouping keys but switch the function to the mean. The multi-index stays, only the statistic changes. One compact table shows the total, average, and count per product. Pandas nests these stats as a column multi-index, which is why headers display as units sold, then sum, mean, count. This line pulls the aggregated summary for the product labeled A from the group table. Because grouped agg uses the product label as its index, the code returns a one-dimensional series showing the aggregated metrics, for example, sum, mean, and count for product A. If the label A does not exist, Pandas raises a key error, and if the group operation had used as index false, the product would be a column instead, and this label lookup would not work the same way. We grouped sales by product, but asked Pandas to keep the group key as a regular column by setting as index equals false. The result is a two-column table with product and sales, where product is a normal column and the data frame has a fresh numeric row index 0, 1, and so on. This format is often easier to merge with other tables because the group key remains a column instead of becoming the row index. In this data frame, the label 0 refers to the first row, so loc returns that entire row as a small labeled series showing product equals A and sales equals 680. Note that iloc is label based. Here the label happens to be the integer 0 because as index created a simple numeric index. If product had been the index instead, this same iloc call would look up the product label rather than the numeric position. This line builds a Boolean test per group. For each region, it sums sales and keeps only those groups whose total exceeds 500. The filter call then returns the original rows that belong to passing groups, not the aggregated totals, so the output is a subset of the original table containing every row from the qualifying regions. The printed rows keep their original row indices, which is why the index numbers may look non-consecutive in the result. In short, groupby plus filter is a way to drop entire groups that fail a group level condition while preserving the underlying row level data. We can create a tiny anonymous function with lambda, for example lambda x plus 1. It does one simple job in one line and that makes the code compact. The same logic written as a named function looks like def add 1x, return x plus 1. Both return the same result when called, but the named function gives us a readable name, a place to add a docstring, and an easier spot to set breakpoints while debugging. In the groupby filter example, the lambda version is df.groupby region. Filter lambda x sales dot sum 500. The anonymous function receives each group as a small data frame x, computes the group total, and returns true or false. The equivalent using a name function is def sales sum greater than 500. Both calls do the exact same work. They run the predicate for each group and keep only rows from regions where the group level sum exceeds 500. Lambda is handy for a one-line function used exactly once and for passing into higher order helpers like map or filter. For example, this lambda code returns 149 and the named version def square returns x2, which produces the same result when used with map. In the groupby context, the following code runs the short function on each group and returns doubled sales for every row in the groups. Pandas may emit a deprecation or shape warning for some uses of apply on grouped columns. When the goal is a per row transformation or a standard reduction, transform or agg is usually the safer and clearer choice. Why pick one form over the other? Use lambda when the logic is extremely short and used only once. It keeps the notebook compact and the intention immediate. Use def when the logic is multi-step, when we want to add a descriptive name or a docstring, when the function will be reused, or when clearer tracebacks and easier debugging matter. Also prefer def if type hints or unit tests are planned, or if the function needs to be serialized or referenced elsewhere. This step shows how to combine two tables by a shared key using merge. Think of it like a SQL join. Rows align where keys match, and how we join controls whether non-matching rows are kept. These are two small tables that share the column customer but list different rows. Notice the overlapping name Alice and the unique names Bob and Charlie. With how equals outer every customer from both tables is kept. Matching names line up on one row where a customer has no match on the other side. The corresponding column shows NaN. The suffixes argument added Q1 and Q2 so the two total purchase columns don't collide. We will study about the join with more details at the end of this class. We use a pivot table to turn long, row-level data into a compact matrix where rows and columns represent categories, and each cell holds an aggregate like a sum or mean. It's like an Excel pivot table in code. This is the long format. Each row is a product region observation with its units sold. Notice laptop appears twice with different regions. Smartphone and tablet appear once. The pivot turned products into rows and regions into columns, and each cell is the sum of units sold for that product region pair. Where a product has no sales in a region, the cell shows NaN because no input rows existed for that combination. The printed matrix shows laptop with 100 in north and 50 in south, smartphone with only a south value, and tablet with only a north value. If a 0 is preferred instead of NaN, fill value equals 0 can be passed to pivot data table when it is created. Now let's practice. It's time to pause here. When you are completed your practice, resume this video. We see a one-dimensional series with a default numeric index 0 through 4 and the 5 numbers as values. The index is how Pandas labels each row. Now the left side shows named labels, Monday through Friday. Labels make selection clearer because rows can be addressed by name instead of by position. Accessing by the label WED returns 30. Using iloc or the bracket label is explicit and avoids counting mistakes when the index is not numeric. The table prints 5 rows and 3 columns. Column names are the keys from the dictionary, and each column can hold a different type. A single column returns as a series with the same row index on the left and the column name shown. This is useful when we want one field as a vector. Loc returns the row whose label equals 1. Here, the index is numeric, so this shows Bob's row with name, age, and occupation. Iloc returns by integer position, which also gives Bob here. Loc and iloc are different concepts. Use loc for labels and iloc for positions to avoid ambiguity later. The table shows missing entries as nan or none. Pandas uses these markers so we can find and handle incomplete rows before analysis. Drop removes any row that has at least one missing field. The result keeps only fully complete rows, a blunt but safe option when incomplete rows cannot be used. Filling replaces missing numeric age with the column mean and missing text with unknown, preserving row count so joins and group summaries later will include these records. Note that doing fills on a copy avoids chained assignment warnings in newer Pandas versions. Sorting by price rearranges the rows from lowest to highest price. Each row's columns stay together so the product price and units remain matched. Grouping by product collapses rows per product and computes the mean units sold for each product. The product names become the index of the result, so it reads like a small summary table. An outer merge keeps every customer from both tables. Matching customers align on the same row, while non-matches show nay-in on the side that lacked a record. Suffixes disambiguate the two identical column names. These practice cells reinforce labeled selection, column, and row access, handling missing values safely, basic sorting and grouping summaries, and the common merge patterns used when combining datasets. Let's move to the advanced Pandas techniques. We summarize subsets of rows by grouping on one or more keys and then apply aggregate functions so the table shows totals, averages, or other statistics per group. We create a small table of product level sales with region and units sold columns. This is the long format where each row records one product region observation. It's the usual starting point for grouping and aggregation. Grouping by product and summing units sold collapses the rows into one total per product. The result is a series or data frame indexed by product labels that shows the total units sold for laptop, smartphone, and tablet. This answers how many units of each product were sold in total. This line produces the same totals but using a slightly different syntax. Select the column first, then call sum. The choice between the two forms is stylistic. Both perform label-aligned aggregation and return the same numbers. The printed total units table restates totals for each product: laptop 250, smartphone 450, tablet 650. Storing the result in a variable makes it easy to use these summaries in plots, joins, or further calculations. Grouping by both product and region produces a two-level index: first product, then region. Each pair shows the total units for that product in that region, so the table answers questions like how many tablets sold in the north versus the south. This multi-index layout is handy when the breakdown across two dimensions is needed. This call returns a compact dashboard per product: total, average per row value, minimum, and maximum. Pandas returns these statistics as a data frame with a nested column index, which makes it easy to compare different summary measures side by side for each product. We usually check the results index and dtypes and decide whether to keep the grouping keys as the index or convert them to columns, for example using reset index, or as index false, depending on whether the summary will be merged back into other tables. Now we combine tables on shared keys. Different join types control whether we keep only matches or also keep non-matching rows from one or both sides. These are two small tables that share the key customer ID. The customer table lists 3 customers and their location. The purchase table records purchases for 3 customer IDs, one of which, ID 4, has no matching customer row. This shape, a customer table and a purchase table, is the common case for joins. An inner join returns only rows with matching keys on both sides. Here only customer ID 1 and 2 appear because they are present in both tables. Inner join is the intersection of the two key sets, useful when analysis requires data from both sources. A left join keeps every row from the left table, the customer list, and brings purchase data where it exists. Customer 3 remains with NaN for product and amount because that customer had no purchase record. Left join is handy when the primary table is the left side. A right join keeps every row from the purchase table and fills customer columns with NaN where no customer info exists. Customer ID 4 appears with NaN for name and location, because that purchase has no matching customer. Right join is just the mirror of left join. An outer join keeps all keys from both tables. Matches align in the same row. Non-matches show NaN on the missing side. The result makes gaps visible and is useful when the goal is a full inventory of keys across sources. We usually confirm that join keys have the same name and dtype before merging and use suffixes when columns share names. The indicator, the true option, reveals which side each row came from, and validate can catch unexpected many-to-many joins. Choosing inner, left, right, or outer depends on which rows we want preserved. Intersection, left priority, right priority, or full union respectively. Let's work with time-stamped data by giving the series a date-time index. This lets us resample into coarser periods, compute moving summaries with rolling windows, and slice by calendar dates very naturally. This is a daily time series. The left column shows calendar dates, and the right column shows the sales values. The index is a date-time index with daily frequency, which is why Pandas prints freq_d. The date range created the 5 daily timestamps, and they became the row labels for the series. Resampling groups the daily rows into weekly bins, and here we summed each bin. Pandas labels each weekly bin by its period end, by default Sunday. So the one weekly value represents the sum of those 5 days and is shown at the week ending timestamp. Resample is how we change temporal granularity from days to weeks or months. A rolling window computes a statistic across a moving window of rows. With window 2, the first entry is NaN because there is no previous value, and subsequent values are the average of the current day and the previous day. Rolling is useful for smoothing and short-term trend detection. Pandas accepts calendar-style string slices and parses them to timestamps. Asking for a single date returns that day's value. A slice from January 2nd through 4th returns an inclusive range of rows. This makes calendar-based subsetting intuitive and concise. Always ensure the index is a date-time index and check its frequency, then resample. Rolling and time slicing behave predictably and support most time series workflows. We represent discrete labels as categorical dtype to save memory and to get faster group, sort, and compare operations. Categories also let us fix an allowed set of values and an order when that matters. This is the initial table of product and region labels in long form. Both columns look like text right now, which is the default string representation in Pandas. Both columns are currently object dtype, which means generic Python objects. Converting to categorical will make operations on these repeated labels more efficient. After conversion, both columns show category dtype. Under the hood, Pandas stores an integer code per row plus the small list of category labels, which reduces memory use and accelerates grouping and sorting. This prints the distinct category labels for product in sorted order by default: laptop, smartphone, tablet. The categories list is separate from the row values and explains the allowed labels. Adding a category extends the allowed labels to include central, but it does not assign that label to any row. This is useful when a new category may appear later or when preparing a consistent category set across tables. Renaming categories maps old labels to new ones and updates all rows that use those labels. The printed series now shows notebook, smartphone, and pad, and the category list is updated accordingly. Use categorical dtype when a column has a limited set of labels and many repeated values. Prefer ordered categorical for explicit order-sensitive tasks. And remember that changing categories changes the label universe, but not row values unless a mapping or assignment is applied. It's time for practice. Please pause here and complete your code. When you are ready, please resume. We grouped by region and computed total and average units. The region labels become the index, and the two statistics sit side by side. For each product, we see total size, typical level, and variability. Sum, mean, and standard deviation form a compact dashboard. Inner join keeps only matching customer IDs from both tables, so we see the intersection of keys. Outer join keeps every key from both sides. Non-matches show up as nay-in on the missing side, which makes gaps visible. Resampling rolls daily rows into calendar months and sums each bin. The timestamp marks the month end. A 7-day window smooths short-term noise. The first 6 entries are nan because the window isn't full yet. Converting to categorical stores labels once with integer codes per row. The categories list shows the allowed values. Adding desktop expands the allowed set, and renaming maps laptop to notebook across all rows. The printed series reflects the new labels. Based on what we studied so far, we will review them using 2 examples. First one is visualization. We'll make simple plots with Matplotlib, then a quick bar chart with Seaborn. NumPy gives us numbers to plot. Matplotlib draws. Seaborn adds clean statistical styles. NumPy handles the numbers. Matplotlib's pyplot is the plotting interface we'll call as PLT. This creates 100 values around 200. Printing wise lets us see the raw numbers we'll plot. We build matching X positions from 0 to 99, so each Y value has a place on the X-axis. This draws a simple line chart of our series and adds a title. The line shows how the random values wander around 200. We shade the area where values sit above 195. The fill highlights high segments without changing the data. These values still center on 200, but vary less because the standard deviation is 3. The shaded rule now uses 190 as the baseline. Linspace creates 100 evenly spaced X values from 0 to 10. Applying sin turns them into a smooth wave. This is the classic scene curve with labels and a title so the axes are clear. We generate a 2x100 array from a normal distribution with mean 100 and standard deviation 5, 2 rows, 100 columns. Seaborn reads the table and draws a clean bar chart directly from column names. This is handy for quick summaries without manual loops. As the second example, we'll create DataFrames, inspect a few rows with head and tail, and add a new column. Pandas gives us labeled tables, so columns can be selected or created by name. Pandas is our table toolkit. We'll use it to build and manipulate data frames. We add a city column by assigning a list with the same length as the data frame. Pandas aligns values by row and shows the expanded table. A fresh data frame is created from the new dictionary. The index resets to 0 through 6. Head returns the first 5 rows by default, which is a quick sanity check on column names, types, and obvious issues without dumping the entire table. Tail returns the last 5 rows, useful when new data was appended or when we want to confirm the end of a file loaded correctly. Both head and tail can limit the count. Let's finish by stitching everything together. We began in Colab and built core Python skills, lists and dictionaries for flexible containers, tuples and sets for immutability and uniqueness, then booleans, conditionals, functions, and loops, so our notebooks could make decisions and reuse logic. We moved into NumPy and treated data as arrays. We created and reshaped them, indexed by row and column, summarized by axis, and used broadcasting so vectors and scalars applied across many values without loops. With Pandas, we stepped up to labeled data. A series gave us one labeled column. A data frame gave us a labeled table. We selected with loc and iloc, cleaned missing values by dropping or filling, checked the types, and then manipulated data. We sorted rows, grouped and aggregated with single and multiple keys, merged tables on shared keys, and pivoted long rows into compact matrices. We also worked with time series, resampling daily data into weekly or monthly levels and smoothing with rolling windows. And we converted repeated labels to categoricals for speed, memory savings, and consistent label sets. In practice, today's exercises mirrored real workflows. Build or load a table, clean it, summarize the parts that matter, combine sources, and reshape for analysis or visualization. As we head into the next modules, keep two habits in mind. Always check shapes, indices, and dtypes before you compute and think in rows, columns, and labels. With these foundations, we're ready to tackle richer data sets and start building models.